Good morning. Welcome. Thank you for being here. My name is Tim Berglund. I work for this company here, Confluent. And what I do at Confluent is I run the developer relations team, or as we call it, the developer experience team, or DevX for short, to sound cool. Up to you whether you think that actually sounds cool. But what my team does is training, evangelism, community, documentation, all of the things that we need to help developers be successful with the stuff we make. And Confluent is the company formed around Apache Kafka. So that's kind of what I do, and that's why I'm talking about streaming data here today. I am new at Confluent. I've been there about 6 weeks. I'm also new in Ukraine. This is my first time here, so thank you very much, JEEConf, for the invitation. Yeah, all right. Shout out to Ukraine. I have been locked in my hotel room so far, which is a terrible way to enjoy this country, but it's okay. Tomorrow I'm going to get out and at least see Kiev. Looking forward to that. All right, let's talk about streaming data. Now, I want to start us with the old story. We haven't always been building streaming data systems. In fact, most of us aren't yet building streaming systems. So just to remind you, this is how we've been doing things for a long time, right? Like at least 20 years. I'm just looking around. Many of you were not writing software when we began using this pattern. We've got a database on the back end. We've got some kind of logic in the middle. We've got something in the front end, which is probably nice, complex, rich JavaScript. Here you go. This is kind of how we build things. There's a database. There's a place where we store data, where it sits. There's a defined schema. You make decisions about the events in the system, and you persist them here. And you process those in the data tier, and you present them in the presentation tier. Like, we all know how to do that. Now, when systems get big, various parts of this architecture get stressed, and so we have different ways of dealing with this. For example, we have sharding. We can take that basic 3-tier system and shard it. Now, this is a time-tested way of scaling an application. A good example of a very popular sharded service would be Slack. So if you use Slack, your Slack organization is one chunk of application, and it might even if it's a small organization, might even share a server with other Slack teams. So there's this little chunk of the application with its own database. So you're building a distributed system when you shard, but you are trying to hide the fact that you're being a distributed system. You're making this little chunk look like it's not really distributed. So, you know, we can shard things. We can get a little more creative. Instead of sharding, we can do something where we're able to cluster our application tier, right? So this now acts like a distributed application tier. The front end is easy to distribute. That's all browsers. We kind of get that for free these days. We have some kind of router in between that's gonna route the traffic to little application shards. What happens when we do this is the database gets real stressed, right? If you've got some giant application cluster, you're probably going to need some kind of next generation scalable database on the back end, which is great. That's like doable now. It's not an exotic thing to do anymore. But there are some complexities with that as well. So without much detail on those, you know, this is kind of how we build things the old way, the slightly new way of doing it. And like a desert, there is a certain stark beauty to those approaches, but I think they fail to acknowledge a basic reality. All right? Those ways of scaling systems, we're missing something there. And what we're missing is that things are always changing. The whole idea of having all of our state in a database is kind of like saying we can stop time and freeze things and say, here's what's true right here. But the reality is we build systems to model businesses where there are events happening to the business all the time. It's a world full of transactions and clicks and movements and measurements and changes in location and all that stuff. All that stuff is changing all the time. And these older approaches, what they do is we want to take all those events and make a decision about what they are and store that representation in a database. It's kind of like a premature optimization. We've got all these events, and we have to design the schema, that's what we call it a schema, and represent that event somewhere in a database. Not only does that database present its own scaling challenges, it gets to be kind of a difficult part of the infrastructure, but it's an intellectual challenge. It's hard for us to be smart enough to make that decision about what that event means and how to represent it. I think we can do better. And this is kind of the basic streaming story. Before we jump into these streaming architectures I want to look at, I want to give you an idea about what I mean by streaming to begin with. All right? So, rather than database and business tier and that kind of thing, backing up a little bit, streaming started with the need to integrate systems, the desire to connect systems. This is kind of the old ETL story. Those are sort of streaming systems where I've got something over here and I need it to get here. And maybe I've got a couple of different sources and I want to connect to those and transform the data a little bit and move it. You know, and it's nice and simple. It starts off simple, like this river. That's just beautiful. Here's one input, there's an output. It's great, right? You can do that. That's kind of how streaming systems get started. They always start simple, but they kind of end up not so simple. It's hard if you're connecting a lot of things. For example, anybody here who's old enough, do you remember ESBs? Enterprise Service Buses. Anybody still using an ESB? Yes, okay, a couple of brave souls putting their hands up. It's fine, we're all friends here. So 15 years ago or 10 years ago, there would have been more hands. So what happened? Why did that not work out? Well, that didn't work out because with ESBs, we decided, okay, we've got all these connectors, and number one, we're going to make everything into XML, which I know it seems bizarre, but that seemed like a good idea at one point in history. Really strange. And also, inside that piece of infrastructure, we put all of our logic in that, or a lot of logic, inside this kind of brittle piece of software. Keep that in mind. I'm going to come back to that idea. In the old ESB stream processing way, all of the logic lived up in this component up here that everything connected to. Turned out not to be a good idea, and we'll revisit that idea in a little bit. The motivation that we're facing now, with just a little bit of history, trying to get us up to speed on streaming things here, the motivation that we're facing now is people are wanting to build these things that they call the real-time enterprise. Now, this is the language that executives use, and you might be able to read, you know, when you fly and there's a little magazine in the back pocket, the in-flight magazine. You don't read those, right? Okay, don't ever, please. But yeah, there could be articles about the real-time enterprise in there. But this is a real thing. At the Kafka Summit 3 weeks ago in New York City, there was a keynote. It was a technical keynote by the chief information architect of ING, the Dutch bank, and he talked about them becoming a real-time bank. This is the idea that all of these financial events that are happening out in the world, you know, which to us look like diverse sources of messages coming from all kinds of crazy systems, all of those are supposed to be presented to the user in a mobile app within a few seconds. Now, if you've ever tried to do a wire transfer, you know a few seconds is not how banking works, right? So this is a major change, and this is kind of where people are going, this idea of rich streams of data all being processed in real time, rather than placed in a database and materialized in some way that we think we can come up with. We keep them as streams, we keep them as event streams, and process them as such. We're going to look at some architectures, some ways people get that done. All of these are, unsurprisingly, going to be based on Apache Kafka. There was a great talk on Kafka yesterday here. Did anybody go to that? The Kafka talk? Okay. All right, good. A good chunk of you. Anybody using Kafka right now? Oh my goodness, look at all of you. All right. Anybody new to Kafka? Okay, well, here we go. It's a good thing I don't have very many slides on this. There'll be more later, don't worry. So yeah, the basic idea is, at its core, Kafka is a distributed message queue. Now, it's much more than that, and by the time I'm done, I really hope that you see that. But at its core, it's a distributed message queue. A bunch of servers acting like one big giant message queue. Applications or producers send messages into the cluster. Consumers pull messages out of the cluster. Now, this cluster is, of course, composed of many independent computers. We call them brokers. And logically, inside the queue, there are lots of little namespaces for messages. We call those topics, which pretty much every messaging system ever has done. So you've got many, many brokers, many topics distributed among those brokers. Data is replicated, you know, all the stuff you'd expect a respectable distributed system to do. It does. And let's look at some examples of how people use this. That's the promise of this talk, is I wanted to show you some real-life examples of people using Apache Kafka and Confluent open source stuff. Some of the companies I'm going to talk about are familiar. Some are probably not familiar to you. But everybody is using Kafka to build a stream processing system. Companies we're going to look at are Yelp, a company called Line Corporation, it's a messaging tool, and a VR company called Altspace. All right, so we're going to look at Yelp, Line, and Altspace. All of this is drawn from public sources, either blog posts that these companies have written or presentations that they've given publicly. So none of this is secret at all. It's all stuff that they've talked about, and basically I have ruthlessly stolen that material and I'm representing it here to you so that we can see examples of what people are doing in real life. Now, each one of them illustrates a little something we should learn. When I get these three on the table, I want to come back and look at what we should be doing when we're building stream processing systems by learning from these examples. Now, let's start with Yelp. Just memorize that URL real quick. Take a picture of it. That's engineeringblog.yelp.com. This post is from last July. It's not one post, it's actually a series of posts. I said July, sorry, May, last year. And a very detailed series of posts on a bunch of really cool things that they did. So Yelp set out to build a streaming backbone. They said, you know what, we are going to go big in streaming. We're going to build our back end as a streaming system. It's also, they don't say microservices a lot, which I appreciate the integrity of avoiding the buzzword. That's always nice. But it is clearly a microservices kind of approach. They've got 150 production services. And they recognized a thing called Metcalfes Law. I don't know if you've heard that before, but that refers to Bob Metcalfe. He's a guy he's getting on in years now. He invented Ethernet. Probably before I was born or around the time I was born, so he's been at this for a while. Cool guy. And he came up with what he called Metcalfe's Law, which is that the value of a network is proportional to the square of the number of things that connect to it. In other words, if there are 10 services, and then I go to 20 services, I don't double the value of my network. I go from you have to square it, so 100 to 20 squared, 400, so it'd be 4x the value of that network. So if I've got this network of services and they're easily able to communicate with one another on this streaming backbone, every service I add is not a linear increase, it's an exponential increase. I've got the square of the number of services that I'm adding. Now, Metcalfe's Law is not super rigorous. This is a little bit cute. right? It's just a way of saying that it's extra valuable to have things connected. I don't think it's super mathematically rigorous. They also discovered that they needed a way for these services to communicate. They didn't like the way REST was scaling, and they found the N+1 problem, which is basically, services returning data and you need to join things. I get one element and it reports a list, and I need to go join that and get details from another service. So it's the good old N+1 query problem. Now in a microservices architecture or a service-oriented architecture, it's even worse. The N+1 problem, Yelp found that led to the temptation for people to develop services that returned bulk data. In other words, basically a microservice that does a query on a database and just returns that as tabular data to the user, okay? Which is, we say in English, absolutely terrible. That's a super bad idea. What that does is it ensures that your microservice system that you thought would be easy to evolve and things would change independently and all that, you'd be super proud of yourself, it was great, was, if I could indulge a cliche, turns out you have made an extremely difficult to deploy monolith. So they saw this temptation. People were building bulk data services, and what that means effectively is you've built a monolith that is awful to deploy. You have to deploy it 150 times to change. So they said, let's not do that. They made some pretty cool decisions. Now, Yelp got started early with an early version of Kafka. Modern day Kafka does all the things that Yelp built. They built a bunch of services that are just a part of standard Kafka now. This is the basic abstraction right here is they wanted a message-based architecture. Every service has a single integration point, and that is a topic in Kafka, and messages are schema'd. They built their own schema registry. They called it the schema registrar, so that consumers of messages or readers of messages could always consult the schema registry, know the schema of the message. Schema could evolve. If you had to upgrade the schema of a message, that would all happen automatically. And of course, we're not going to dive into the details of how they did that, but they built a schema registry. Now, this is a part of contemporary Kafka. There is a schema registry. That's a thing that you can have in the open source version. They had another problem, which is that as much as they like streaming data and they're trying to commit to streams, some of their services still maintained databases. Now, why is that? Is that just an incomplete commitment to a streaming data architecture? Or is there actually a good reason for that? Well, the reality is sometimes it's perfectly okay for a service to maintain a database. That's not a bad thing. You can do that. But in the migrating into this streaming data world, they found that they had a lot of tables out there, and they discovered a truth called the stream table duality. Now, as you read about streaming data architecture, you're going to see that phrase again, the stream table duality. What that means is you can represent a table as a stream and a stream as a table. You can transform one to another. They built a system that listened on the MySQL bin log. So that's the actual log of changes internally in the MySQL database. They would watch the bin log in a database, and anytime there's a mutation of any kind, you turn that into a message and put it into a Kafka topic. Okay, cool. So that's stream table duality. Any change to that table becomes an event in the messaging system. On the other side of things, you can take those events and materialize them in a table if you have to. We're not going to go into that end of things too much, but when you look into the Kafka Streams API, you can see that kind of thing happen. So you'll see this concept of the stream table duality. That was a thing Yelp discovered. And they built this system to make this happen. In contemporary open source Apache Kafka and Confluent open source extensions, this kind of stuff can be done, again, for free. You don't have to build a bunch of stuff custom by yourself. There is a tool called Kafka Connect that's a part of Apache Kafka that'll let you read from any JDBC database and turn it into events. All right, so what have we got here? We've got the integration problem. We've got stream table duality. They had to solve that problem. And also, they wanted to do computation on these events as they flow from one part of the system to another. Having committed to a streaming data backbone, you don't want to take those messages off a topic, stick them in a database, and then do computation on them in a database. You want to take those messages off of a topic, do computation on them, and put them in another topic, and then take them from there and do computation on them and put them in another topic. You want to keep the computation close to the message, which is what they wanted to do. And again, being a little bit over themselves, or a little bit ahead of themselves, they realized around 2010, or a little bit after 2010, MapReduce, which, remember, seemed fun then. So 2002, XML seemed like a great idea. 2009, MapReduce sounded really cool. Like everybody was trying to understand it and do word count examples and stuff like that. And then people who were actually trying to build real systems with MapReduce hated their lives. And we don't like that when we make tools that causes us to hate our lives. And they found that out. They found that that was a very difficult system to use. They had built this messaging system. They had this nice schema layer. They had schemaed messages. What are we going to do? Well, at the time, in kind of the early 2010s, Storm was an event processing framework developed at Twitter that was sort of the popular thing. Now, Yelp has a commitment to Python. Storm didn't support Python real well. And so they wrote their own, as they like to do. Now, these days, Storm still is in use, but in terms of its community, it seems to be winding down. So Yelp probably made a good call not to commit to Storm back when they did this. What they did, though, is they built a very simple system. Any Storm users? Okay, did I insult you when I said that it's... Okay, I apologize. Okay. Anyway, many hands did not go up. There are two terms in Storm, a spout and a bolt. All right, a spout is basically an interface that you implement that is a source of data. You pull data in from somewhere. A bolt is another basically interface that you implement that processes messages from a bolt or from another spout, or from a spout or another bolt. So the wise guys at Yelp decided they would just create one thing called a spolt. I suppose they thought that was funny. And there you go. This is their internal Storm. It's a very simple message processing framework. You pull messages off of a topic, process them, stick them into another topic. All right? And anybody could write that. I think we can all sort of imagine, even if you've never looked at the Kafka API, you can kind of imagine what a pub/sub API might be, and you could build this in some simple form, which they did. And again, they did this before the Streams API for Kafka was released. The Streams API for Kafka is only about a year old, and at present, Yelp is, according to public statements in their engineering blog, thinking about refactoring to that Streams API for Kafka rather than maintaining their own thing. And that's probably the right thing to do. But they recognized that they had this stream processing thing that they had to do. So what do we see from Yelp? We see as an abstract concept they believed that microservices were a good idea. They believed that that approach to services lends itself to an evolvable architecture. You have many small, independently developed, independently deployable services. You've got fairly strict schema management that allows you to evolve and version and release those services independently. That gets you access to Metcalfes Law now. It's more valuable to add, it's more than linearly valuable to add another service to your system. So commitment to the streaming pipeline, that was a good thing for them. They saw the stream table duality. You still had databases in your world, and you had to be able to turn those into messages and turn messages into database. They saw that schema mattered, and we see that they were ahead of the game. Before Kafka had a thing, they would build it. And so in some cases now they have their own proprietary version of things when the Apache project has its own stuff. Lest you accuse them of the not invented here syndrome, I don't think that's fair. I think they were really just ahead of the game, and they would be happy to use open source things once they exist. They just were forward-looking. All right, so that's what we see from Yelp. We'll come back to that. Let's look at our next example, Line. Now, Line is a mobile messaging platform, and they've got a goal. They don't want their take on the world is they don't want one global messaging app. They want to build a set of services that allow people to build localized, kind of culturally adjusted messaging tools for wherever the tool is being used in the world. Rather than everybody gets to use WhatsApp, they want to be customizable. So they're building a set of services that get to be mixed and matched to build some sort of indigenous messaging framework. That's sort of their vision. And again, their engineering blog, ruthlessly stealing this whole account from there. Hopefully I'm representing it fairly. But here we go. What did they want? Well, they have these messaging systems on the back end, and they made a commitment to a streaming data platform. Now, they're a messaging system, so in a sense that seems cheap, right? Of course they can do streaming data. It's easy for them. Everything's an event. The rest of us who are dealing with mutable state and have this database tradition that we're dealing with, it's kind of hard to make that leap. It's a little easier for them. So this is a nice, easy example to think through. Now they had kind of a legacy system that they had built themselves, but they wanted to pick a framework. And so they looked around at stream processing frameworks. And there's a good lesson to be learned here. They looked at Apache Samza. And they said, okay, let's look at Samza. They said, well, it uses Yarn. And Yarn kind of comes from a batch tradition. It's sort of it's built around batch processing. That didn't look too good. And they thought it had some JVM heap issues, and it seemed operationally complex. And they did not want to go with Yarn because, with Samza, because Samza is a cluster that wants to do that stream processing off here in the cluster, just like Spark Streaming would do, or Flink, or any of those. These are systems that are extremely well-respected systems, very widely deployed, but they take that approach of saying, well, here is our cluster where the stream processing gets done. We take our logic and we put it off in this thing over here. What does that sound like that I mentioned before? Sounds like an ESB. Now, I'm not going to stand on a stage in front of colleagues and say that Spark Streaming is an ESB, because I would deserve whatever trouble I got for that. It's not true. Spark is certainly a very powerful and widely respected framework, and its streaming API is great, but careful there. There's a little bit of a similarity where if we're building a streaming data architecture, we're saying, hey, wait, let's put all our code over in this thing, and anytime I need to change stream processing, I need to change code in this thing. hey, maybe it works. Maybe it's modern. Maybe it supports modern deployment automation techniques and everything's fine. Maybe it doesn't. We just want to pay attention. We made a mistake 15 years ago with that architecture. Let's make sure we're not making that mistake again. So they saw that with Sam, so they didn't go there. Then they saw, this is just from a little over a year ago, Kafka Streams, or the Streams API for Kafka. And they said, okay, cool. This is a library. It's not an execution framework. So a lot of people are surprised by this when I tell them that Kafka Streams is effectively a jar. So Kafka is data infrastructure. I spin up computers and I install Kafka on them, and I spin up a Zookeeper cluster and I make this thing, and there's my distributed message queue. Kafka Streams is a dependency that I declare, and I build my application, and the stream processing code runs in the context of that application. That's surprising to people when they first encounter that idea. Key architectural principle here, though. And the guys at Line really liked this because it was lightweight. Masterless, all it does is it reads from a topic, writes to another topic, does the stream processing in the middle. And this is what some of that code looks like. I build a kind of a helper object called the KStream builder, and I use that builder to read from a stream. That's that next line there, stream text lines topic. Now I've got some data to play with, and I can convert all of the words to uppercase better than word count, folks. Cooler example code than word count is uppercasing all the words. And then I take those uppercase words and I write them to another topic. So it's your basic, it is a Fluent API. I'm not really using it in a Fluent way here, but your basic Fluent Java API, super simple to use, and all that computation is happening in the context of the application. Because usually the actual stream processing work that you have to do in the context of an individual microservice is fairly lightweight. So the idea of taking the stream processing code and moving it off to some cluster to run over there, and then having to do all the work of shipping the code and managing the jobs and all that kind of overhead, usually isn't worth the money. Usually the computation you're doing on the stream that you care about in your application is lightweight with respect to the amount of work that the application itself is doing, or the microservice itself is doing. So it doesn't, if you think about making the computer warmer, you don't get that much warmer with the stream work that you have to do. And these guys at Line discovered this was a super cool thing. I'm going to skip that in the interests of our time. Yeah, and so they had, for example, this one thing that they had called the loopback replicator, and they talk about this in their engineering blog. It got 1 million messages a second coming into it. That's a lot. All right. There were some other services that just wanted a filtered view of that. Okay, the most trivial stream processing you can think of is look for all these client messages coming in and write into this other topic only the client messages that have to do with, say, contact list changes. Easy enough, right? That's just a filter operation. Easy to do. And sure enough, they could get that work done. And they could get more complex work done as well. I won't walk you through all of this, but essentially you've got a partitioned topic here. So this is a topic that's running on multiple brokers because no one computer can handle all the traffic. You've got a bunch of computers cooperating to handle this load, and multiple machines also processing that input, sending it to another topic, another partitioned topic for mutation and storage in HBase later on. And this stuff, you see up here, this box up here is Kafka. This is the message queue. This is your data infrastructure. Kafka Streams, this is just my application. That's it. All right, classical Kafka Streams implementation, and really what we see from these guys is they timed it right, and rather than build, they bought. And of course in open source, buy means download. All right, these guys gave a really cool talk at the Kafka Summit just a few weeks ago in New York City. And they are a VR company, obviously, and another one that built from the ground up using Kafka Streams, and a classical example of stream processing. Note, you should be seeing a trend here. Kafka is not just being a dumb pipe. It's doing a lot more than that. All right, what do these guys do? Well, they're a social VR platform, so interactive games, music events, and things like that. They did a virtual tour of a volcano. It's hard to do in real life. Tried to fly my drone over a volcano once. Wasn't allowed. I was very upset. Land of the free. Not really. Anyway, they've done like a virtual Super Bowl party, virtual tabletop D&D. You're like, wait, couldn't I just do D&D in the browser? Why? But hey, this is more fun this way. And music events. Reggie Watts. They've done virtual concerts. They use a game engine called Photon, which is a multiplayer online gaming engine. It's kind of like the multiplayer version of Unity, if you're familiar with Unity in console games. And they wanted to do real-time things. They wanted to capture events for playback later. They want to do both of those. And they succeeded. So, and this is ruthlessly stolen from their own slides. Thank you, AltSpace. You guys are awesome. They could capture in their client incoming events, a little bit of processing, send them back to another room. So, for example, the Reggie Watts event, you can't have a good VR concert experience with 10,000 people in a club. You want to recreate the comedy club experience, which is maybe 150 people in a room. It's a room like this and kind of smoky maybe. In the good old days, we can't do that in America anymore. But and maybe there's 10,000 people out in the world, so you need to be able to make many, many rooms. Well, and here you go. You can do that with this system. Also, you want to be able to save it for playback later. Well, they had a system that would just dump those messages into S3 using Kafka Connect, and then later on, we could read those in from S3 in a kind of a carefully timed fashion and feed them back into one of the VR rooms, like this. The playback there. So, how are we on time? This should kind of get you wondering what's the right way to do this? What's the right tool set to use? The commonalities we've seen between these three examples are everybody seems to want to be doing computation on messages as they flow through the system. Our impulse, our default mode, the training we have gotten, the practice we have gotten is we take the data, we do a little something to it, and we stick it here in a database, in a place, and it sits there. If there's a lot of data, that ends up being a cluster. It's HDFS, it's Cassandra, it's whatever. Fine. If you've got a lot of data to stick somewhere, you need a cluster. Because we made clustered file systems and clustered databases, we got in the mode of this batch computation process that would do all the compute near the data, and we had Hadoop, and we have Spark, and we have things like that work great. And we kind of got stuck there. We got stuck thinking all of our data needs to go in a database, all the computation needs to happen on it there. That's probably the wrong approach. So what I'll call the proper approach is something like this, where we've got Kafka in the middle, and that is our event bus. That's all of our messages. And anything that comes in or goes out, anything that touches the system, this is our system. We've got an API called Kafka Connect that makes it very simple to connect to any of these things. A key value store, we can pull data in from any monitoring system virtually that we want. We can dump data out into Elasticsearch. We can dump data even into Hadoop if we need to, if we want there to be offline analysis and a place to stick all of our data. This becomes the approach that we take. Not only do we do that, but we try as much as possible to avoid putting the data in a static location in a database. Remember the pitfalls there. Number one, it gets kind of big, and that's hard to do. There are databases that handle it well. I happen to know and love Cassandra, and that's a database that gets big, has no trouble getting big, and works well, but you make a lot of sacrifices when you move to a distributed database. So as much as possible, you keep your data as a stream, and you process you do the computation in the stream. Now, this topic, Kafka Streams, is of course worth an entire 50-minute talk all on its own. I just want to get it in your head that in these architectures, everybody did this. Yelp wrote their own, but Line and AltSpace VR used Kafka Streams, this lightweight library that puts the processing with your service and keeps that code. You already know how to deploy microservices, or if you're doing microservices, that's the whole point, is that we deploy them in an automated fashion. They're very easy to change. And so we get all of these advantages basically for free. So instead of this complex thing where even with Kafka, this is basically a Lambda system here where events come in and some of it goes into batch storage for analysis there, and some of it goes into real-time processing. We don't even really need to do that anymore. We get a vastly simplified architecture where requests, or really events, come in, they're processed, they could be stored in topics, they can be dumped into external sources, external sinks as necessary, but all that work happens in real time. You're not imposing delays, and you're not fooling yourself into thinking that you can design the right decision, and you can make the right decision and make a commitment as to what that event means. You can just put the event into the bus, and anybody who needs to consume it, any future service that you deploy, gets access to the value of that event. You've not reduced it into a row in a table and made all those decisions ahead of time. It just gets to be its raw self. Now, if you want more on this, rather, if you want to play, you can do confluent.io/download. If you want more, you can check out meetups near you right here. This is a thing that my team runs, and so is this, our Slack community, and would love to see you in there. You may occasionally even see me in there typing things into a Slack channel near you. Everybody, thanks a lot. See you later.
Not really. Yeah.
What's our time, though?
Just one question. I'm curious. Like, I'm a big fan of Spark Streaming, and I'm a big fan of Kafka Streams. But just one point of notice that you haven't mentioned. I think that Spark Streaming has two big advantages in comparison to Kafka Streams. It's like failover, automatic re-execution of the job if something failed, and more dynamic resource allocation. You can have Mises or Yarn integrated, and for instance, for one particular streaming job, you can allocate more resources, while with Kafka streams, like both those activities, like failover and resource allocation will be on your side, because that's your application, you need to handle it.
Resource allocation, yes. Failover, no. The different tasks in the streams will manage different workers and manage the state inside the cluster. So it does a little bit of failover. Resource allocation, fair point. The argument there is that you already know how to scale your service. And usually the computational burden of the stream processing is not that big, right? Like you do the stream processing in a Spark cluster because you already had a cluster because you started with HDFS. And the Kafka streams argument is that's an unnecessary holdover and unnecessary complexity. So if you do need to scale as a result of the stream work, you have a fair point.
Yeah, that's my responsibility to scale as much applications as I need to do that.
Because you're going to have to anyway.
Okay.
Always. That's kind of the argument. But great questions. All right. Sorry to cut off questions like that. That was terrible of me. But thank you for being here. Hope to see you later.